Today we're going to be seeing what happens when I shine the world's brightest flashlight, 100,000 lumens, on a Crookes radiometer. So if you don't know what a radiometer is, it's a way to measure the amount of radiation hitting an object. It was invented in 1873 by Sir William Crookes. So look what happens when I just shine a flashlight on it. It slowly starts moving. So in this way you can quantitatively measure the amount of radiation that's hitting it. The brighter the light, the faster it will move. Okay, we're gonna start out at 700 lumen. All right, 700 lumens spins it appreciably fast, better than my small flashlight here. Turn it up. Okay, this is 2,000 lumens. Turn it up again. Whoa, 5,000 lumens. Look how fast it's spinning. Okay, 30,000 lumens right now. Okay, here we go, 100,000 lumens. 3, 2, 1. Whoa, 100,000 lumens. I think it's reached its max speed in there. It can't go any faster. Okay, now that was pretty cool, but how does a radiometer actually work? Is the light actually bouncing off it and causing it to recoil and spin the other direction? So when it was first invented, Crookes, the inventor of it, he actually put forth the explanation that it's just like a water wheel. So when you pour water on a water wheel, it causes it to start spinning due to the pressure of the water hitting the wheel. So he used that same logic with light. He said the pressure from the light is hitting the vanes, causing it to spin. So it hits the vanes in there and pushes it around in a circle, just like water on a water wheel. He even ran that explanation by James Maxwell, who approved of the explanation. He was just excited that there was something that showed radiation pressure happening. But it turns out there's a problem with that explanation, and it has to do with the momentum of light. If that were the true explanation, then the radiometer is spinning in the wrong direction. And the reason for this is when something bounces off something, it imparts more momentum to the thing it hits than when it sticks to it. So let's say this photon has a momentum of 1x, and this has a momentum of 0 because it's not moving. So when the photon hits it and gets absorbed, now this total momentum can still just be 1x. It can't have any more or less. So the whole system will have a momentum of 1x. But if a photon of light bounces off of it, that means that once it bounces off, the momentum is now in the negative direction, so it's negative x. So that means this has to now have a plus 2x momentum. So that means when it bounces off of it, the radiation pressure should be twice than when it's absorbed to it. So for the radiometer, that means that the white side is reflecting it more than the black side. So the white side is the thing that should be getting pushed more, so it should spin in the opposite direction. So if that's not the explanation, then how is it actually working? Well, it turns out the way they make this is the inside of this is rarefied air. That just means that it's at a low pressure inside of there. It's not a full vacuum, but it's really low pressure. So if this were spinning due to the pressure of radiation hitting it, then if we vacuumed out all of the air and made it a better vacuum, then it should spin even better because it would have less air resistance. But they found that when they make it a very good vacuum inside of there, it doesn't spin better. In fact, it doesn't spin at all. So that led the physicists to believe, well, it must have something to do with the air inside of there. What if it's a result of the light hitting the black vanes, and that causes the air to heat up and expand, and that pushes the black vane and turns it in a circle? And this explanation is actually the one that I've heard the most. And it turns out that explanation is also wrong. The problem with the pressure explanation is that even though the pressure is increasing, which means the molecules are moving faster and create a greater net force on the black side than the white side, the problem is that they block other molecules from reaching it. So the ultimate result is that they nullify each other out, and there's no net pressure on the black side as opposed to the white side. So they push harder, but they block other molecules from getting there, so they don't end up pushing harder. In fact, James Maxwell, fearing that he was going to be wrong again when this explanation was put forward due to the expanding gas, he did the math on it and found that it wouldn't actually cause it to spin. There's no net force causing it to spin in any one direction if the gas just heats up and expands next to the black in there. So what is the real reason that a Crookes radiometer spins? So the real reason that a Crookes radiometer spins is called thermal transpiration. And it's actually due to the forces on the edges of the vanes and not the main flat surface of the vane itself. So let's say we're looking at a cross section of the vane, and this is the cool side and this is the hot side. So this is the black side and this is the white side. So due to this side being black, it's going to get hotter than the white side. It absorbs more of the radiation. And so this side is going to heat up and cause the gas around it to move faster. So the gas on the hot side is moving faster than the gas on the cool side. So the length of my arrow is going to show how much force it has. So the molecules on this side that happen to hit the vane going this direction are going to have a high force, and the ones on this side are going to have a low force because they're colder. Now if you add up both of these vectors, then that means you get a force in this direction. So it's not due to the expansion of the gases per se, but it's actually due to the speed of the hot gases on the black side. And that causes a discrepancy in the forces on the edges of the fins, which causes it to be pushed in this direction. Now the really interesting part about a Crookes radiometer that you might not have known is that you don't have to use light to make it spin. You can actually just use warmth or coldness. For example, if you just put your warm hands on it or pour warm water on it, then it causes it to spin in the same direction it spins when you shine light on it. So the glass heats up and emits infrared radiation that you can't see, and the black side picks that up more than the white side, and it heats up the air around it on the inside, and again, due to thermal transpiration, it causes it to spin in the direction of the black side. But what's really interesting is if you put an ice cube on it or put it in the freezer or something, it actually spins in the opposite direction. And that's because remember that things that are black, they absorb radiation really well and they emit radiation really well. So when you put it in the freezer or put an ice cube on it, that means that the vanes are now hotter than the glass. And so the black side is going to emit its infrared radiation better than the white side. So it's going to actually cool down quicker than the white side. So in this case, the black side gets colder than the white side, and the white side heats up and causes it to spin in the opposite direction. And thanks for watching, and I'll see you next time.